Look around you right now. You're surrounded by color: red, green, yellow, orange, brown. But take a closer look. How much blue do you actually see? Blue flowers are uncommon. Blue fruits are almost non existent. And blue animals? They're so rare that when we do see them, a blue butterfly, a blue jay, a blue poison dart frog, we stop and stare. It feels special, almost unnatural. So here's the question. We live on a blue planet. The sky is blue, the ocean is blue, yet somehow nature struggles to make anything truly blue. Why is that? The answer has to do with chemistry, light, and one of the strangest tricks in the natural world. To understand why blue is so rare, we first have to understand how color actually works in living things. Most of the colors you see in plants and animals come from pigments. Pigments are molecules that absorb certain wavelengths of light and reflect others. The color you see is the wavelength that bounces back. Chlorophyll in leaves absorbs red and blue light, so plants look green. Carotenoids create the orange in carrots and the yellow in bananas. Melanin gives us brown, black, and tan. These pigments are everywhere in nature. They're easy to make. Just a few simple chemical reactions and you've got color. But here's the problem. Making a blue pigment is incredibly difficult. The molecules required to absorb the right wavelengths and reflect pure blue light are complex and chemically unstable. They break down easily in sunlight. They require rare building blocks that most organisms don't have easy access to. For most of evolutionary history, nature simply couldn't figure out how to make blue. And yet, we do see blue in nature. So if it's not coming from pigments, where is it coming from? This is where things get fascinating. Most blue in nature isn't a color at all. It's an illusion. It's called structural color. Instead of using pigments, many blue organisms use microscopic structures on their surface that manipulate light itself. Think of it like this. White light from the sun contains all the colors of the rainbow mixed together. When that light hits a specially designed nanostructure, the structure scatters the light in a very specific way. It cancels out the reds, yellows, and greens through a process called interference. And it amplifies the blue wavelengths. The result? You see brilliant, vivid blue, even though there's no blue pigment anywhere. Blue jays are a perfect example. If you were to grind up a blue jay feather and look at it under a microscope, you wouldn't find any blue chemicals. What you'd find are tiny air pockets arranged in a precise pattern inside the feather's structure. Those pockets act like microscopic mirrors. They scatter light in just the right way to produce blue. If you crush the feather and destroy the structure, the blue disappears. It was never really there, it was engineered by the shape of the feather itself. Butterflies do the same thing. The shimmering blue wings of a morpho butterfly are covered in layers of microscopic scales. Each scale has ridges so small you'd need an electron microscope to see them. Those ridges reflect and interfere with light, amplifying blue and canceling out everything else. Again, no pigment, just physics. Even the few blue flowers that do exist often use a combination of red pigment and structural tricks to fake blue. Cornflowers, delphiniums, and morning glories rely on a pigment called anthocyanin, which is naturally red or purple. But they pair it with specific cell structures and pH levels in their petals to shift the perceived color toward blue. It's not pure blue, it's a carefully controlled optical hack. So why did nature go to all this trouble? Why build microscopic structures instead of just making a blue pigment? Because structural color has advantages. It doesn't fade. Pigments break down over time, especially in sunlight. But a physical structure that manipulates light can stay vibrant for years, even decades. It's also incredibly efficient. You don't need rare chemicals, you just need to arrange what you already have in the right pattern. But here's the catch. Building those nanostructures is incredibly difficult. It requires precise genetic instructions and exact spacing at a microscopic level. If the structure is off by even a few nanometers, the color changes or disappears entirely. That's why structural blue is rare. It's hard to evolve. It takes millions of years of trial and error to get it right. And that brings us back to the original mystery. Blue is rare in nature because making it is hard. Chemically, it's unstable. Structurally, it's complex. Most organisms simply don't have the tools or the evolutionary pressure to develop it. So when you see a blue morpho butterfly or a blue macaw or a rare blue flower, you're not just seeing a color. You're seeing millions of years of evolution solving one of the hardest problems in optics.